Hello! Here are some review terms which you should familiarize yourself with before you continue through the rest of the video. Feel free to pause. And here are some more terms specifically regarding the structure of amino acids. So, both the amine of the N-terminus and the carboxylic acid of the C-terminus are considered weak acids and are weak acid functional groups and can act as buffers. The amino residue exemplifies what's called a Zwinner ion, which has a net charge of 0. It transitions into a positive species via the pK1 arrow and occurs whenever the pH is lower than the carboxylic acid's pKa. This means that the solution is more acidic than the carboxylic acid. The carboxylate group will gain a proton from a concentrated acidic solution, which neutralizes its negative charge, but it maintains the positive charge on the amine group. The Zwinner ion will transition into a negatively charged residue at a higher pH. It's represented by the pK2 arrow. The amine group will lose its additional proton in a solution which is relatively basic, so whenever the pH is higher than the pKa of the amine group. This is because the solution is more basic than the amine. The exact pKa value for both the N and C terminus are dependent on the amino acid's R group. This is exemplified by the 3 amino acids below. We can see that glycine C terminus has a pKa of 2.34, while threonine has a value of 2.11. Your textbook should contain a table which lists these properties associated with the 20 common amino acids. So, as we saw before, carboxylic acids and ammonium are both examples of weak acids. The same applies to R groups, which have acidic functional groups. So, glutamic acid's R group has a pKa of 4.1. The glutamic acid is in the HA, or acidic form, on the left of the reaction, and the glutamate is in the conjugate base form on the right side. Lysine's R group has a pKa of 10.8. Its conjugate base is on the left side of this equilibrium, and the acid is on the right. Basic amino acids are ones which have an R group that is protonated whenever the pH is below their pKa value. So whenever pH is greater than pKa, the R group is neutral, which is in the conjugate base or A- form. Whenever pH is less than pKa, the R group is positively charged and in the acid or HA form. Lysine and arginine are both positive at physiological pHs, while histidine has the ability to act as a buffer. Acidic amino acids are ones which have an R group that ionizes above its pKa value. So whenever pH is greater than pKa, the R group is negatively charged and in its conjugate base form. Whenever pH is less than pKa, the R group is neutral and in the acid form. Both glutamic and aspartic acid have the ability to ionize at physiological pHs. Tyrosine and cysteine have the ability to ionize, however, are usually not involved in this. Tyrosine is usually neutral at physiological pH, but has the ability to act as an acid at a very high pH due to its high pKa value. Cysteine can theoretically ionize near physiological pHs, but it's usually involved in disulfide bonds or other post-translational modifications that prevent the buffer activity of its R group. Amino acids with ionizable R groups have an additional species and therefore have an additional pKa value. This is important to note whenever we're trying to determine the net charge of peptides. Once again, a list of these should be in your textbook. So here we can see the charges of each species in a section of a theoretical titration curve. So for glutamic acid, it has 3. So whenever the pH is less than pK1, we see a species that is positive. Whenever the pH is greater than pK1 but less than pKr, we have a neutral species. Whenever the pH is above the pKr or pK2, we have a charge of -1 or -2, respectively. Non-ionic amino acids like glutamine on the right only range from +1 to -1. The Henderson-Hasselbalch equation is used to determine the net charge of an amino acid at a specific pH. The pH describes the acidity of a solution, and the pKa describes the acidity of the molecule. This determines the ratio of molecules which will act as either the acid or conjugate base in the solution. If we solve for the ratio of conjugate base per acid, it's 10 raised to the power of the pH minus the pKa value of that specific amino acid. If we wanted to do this with histidine as an example, which has a pKa of 6.5 and it was in a solution of pH 7.2, we would subtract 6.5 from 7.2 and raise it to the power of 10. This gives us a ratio of about 5 to 1. So, from this ratio, we can determine that the percentage of each species at that pH, and therefore the general charge. So when considering the ratio of 5 to 1 at this pH, the acid form is the +1 species, and the conjugate base is the neutral species of histidine. So for every 6 histidines, 5 will be neutral, and 1 will be positive. This gives us about 83% neutral and 17% positive. So we have a net charge of about positive 0.17. If we do the same for glutamic acid, we can see that almost all the species are in the conjugate base form with a charge of -1. This is because the pKa value of this amino acid is much lower than the pH that we are looking at. The Henderson-Hasselbalch equation can also be used to determine the charge of an entire peptide based on the summation of all the charged residues. So, If we want to consider the peptide leucine, tyrosine, glutamate, arginine, we can know that the N-terminus and the arginine have the potential to be positively charged, while tyrosine and glutamate and the C-terminus have the possibility to be negatively charged. So to find the net charge, we will calculate the charge of each independent residue that has a possibility of being charged at this pH. So we're looking at pH 9.5. So the N-terminus has a pK of 9.6. So using the Henderson-Hasselbalch equation, we can find that about 56% is positively charged at this pH. So if we multiply positive 1 by 0.56, we can get about a charge of positive 0.56. The same applies for tyrosine, which is going to be negatively charged. So once we add all these together, we get a net charge of about negative 0.65 at pH 9.5. The isoelectric point is the pH where the peptide we are looking at, or the amino acid we are looking at, has a net charge of 0. So whenever the pH is higher than the pi, it's considered a negative species, and whenever the pH is lower than the pi, the molecule will be a positive species. The pi is a net charge of 0. This does not mean that there is no charge, it just means that the positive outweighs the negative. So for glutamine, we take the mean or average of the two pKa values, giving us a pi of 5.65. For ionizable amino acids, they have different pKa values. So we have to look at the mean or average of the two pKa values surrounding the neutral species. So for histidine, it's 7.84, and for glutamic acid, it's 3.15. So let's look further at histidine. So if histidine's isoelectric point is 7.84, and let's say we put it into a solution that is pH 9, you'd expect the molecule to be negatively charged since the pH is greater than the pi. So using the Henderson-Hasselbalch equation to confirm this, it can be calculated that at pH 9, about 40% of histidine has a negative 1 charge. Therefore, this statement is correct. Thank you.